John, you've been on the go ever since you were born, and I imagine few people in the world today have traveled as much as you have. Now why?
Well, I don't know. I suppose some of us are cave dwellers. Some of us live in houses. Some of us like to be loose-footed. I'm a rambling man.
Okay, so here's the Kerbal Space Center. The rocket takes off, flies downrange, stages, and then the second stage continues on to orbit. And the way we're going to simplify this problem dramatically is by having the rocket do a boost back burn that cancels out all horizontal velocity. So it'll still have some vertical velocity, it'll flap a little bit like this and then fall down. And the way this will simplify things dramatically is it'll mean that aerodynamic resistance can be ignored, just thrown out entirely, because it'll be only a small effect, and in the final descent, the rocket can steer using fins. And so it's a gross simplification, but it gets the job done. Just ignore air resistance, cancel out horizontal velocity, so we don't have to do, find the time it takes to follow a parabola. Just have to find the time it takes to fall straight down, which is a pretty simple problem. And the reason I want to do this is not because it's the most efficient way of doing this, but just so that I can simplify into terms usable in kOS a lot easier than otherwise. So, got the altitude here, the apoapsis. That's the highest point in the trajectory, and the time to apoapsis will be ETA time, and that's something that is built into kOS. And then the time it'll take to fall will be equal to, after a quick Google search, just any object falling without air resistance is the square root of 2 times the altitude divided by g, in this case 9.81 meters per second at the surface anyway, and on Earth at like 70 kilometers at apoapsis here, g would be 2% lower, but on Kerbin, g would be, I don't know, like 20% lower. So this is a gross simplification, but I want to avoid differential equations, so I'm just going to use this gross simplification. The game here is we want the time to fall here, this time, to be equal to the time it takes the planet to rotate under the rocket here as it flies. And Kerbin rotates at 175 meters per second. So we want the Kerbal Space Center to rotate with the planet under the rocket as it flies in the same time it would take to reach apoapsis and then fall down. So the expression for this would be the time it takes is equal to ETA time to apoapsis plus the time to fall, and we want to set this equal to the time it would take to rotate, for the planet to rotate the Kerbal Space Center this distance where the rocket is. And let's call that distance d. That's what we want. So for this, that'd be the distance divided by 175 meters per second. And we can set this equal, these two terms equal to each other, because we want that time to be the same. We want that time to be equal. So we'll set these two terms equal to each other. And if you solve for the time it takes to fall, since we know what that is, that'd be time to fall is equal to the distance divided by 175 meters per second minus the time it takes to reach apoapsis in this case. And so let's try to simplify this for altitude, the apoapsis rather, because we can run an expression in kOS to find the apoapsis we need so that these times will be equal. We can have the rocket burn a bit to reach that apoapsis. And in testing, I've determined that normally it only needs to burn like a couple hundred meters per second to adjust that apoapsis so that the timing is perfect. Again, this depends on the launch here. This is a simplification, but if we solve for the apoapsis here, we can square both sides, and that would be 2 times altitude divided by g equals the time to fall squared. And so the apoapsis we need is g divided by 2 times the time to fall squared. And we know what the time is to fall that we need. So if we substitute this expression in, then we'll find the apoapsis we need. So the apoapsis is the time we need squared. So this is the way we all time it, like merging onto the freeway. You're trying to slot in between cars. For your apoapsis here, you want to raise it just a little bit so that it'll fall back down and back onto the KSP. This isn't perfect because what if we needed to lower the apoapsis so that it'd fall back onto the KSP? I'm not going to write code for that case because in testing I found that most of the time you just need to raise it a little bit. It just depends on how much you need to raise it. For the landing itself, though, we're going to do a suicide burn, and then once the suicide burn gets us down to like a few meters per second, we'll just keep that speed constant. So let's find the speed, or rather the throttle setting we need to keep speed constant after the suicide burn. And then I'll also have to solve for the height for the suicide burn. But the force we need to fight against gravity, just kind of hover, would be force equals mass times acceleration, or in this case, fighting against gravity. So that'd just be g, 9.81 meters per second per second. And another way of expressing the force we need in kOS is some multiplier times the thrust of the rocket, the impulse of the engines. So I'll just say the thrust we need is some multiplier, kOS, this number in kOS is between 0 and 1, times the thrust of the engine equals the mass of the rocket times g, the acceleration due to gravity. This doesn't change, at least very much anyways, because we're just talking about running the engines at sea level. So when I substitute in the thrust numbers, I have to remember to use the sea level thrust. The mass does change though, and so we want to use the lock command in kOS, so it keeps updating, it keeps on checking what the mass is, and it keeps on adjusting the multiplier here so that it'll consistently stay at the same speed, roughly. And so what that multiplier is mass times 9.81 meters per second. And I kind of forgot, actually, kOS expresses mass in tons. I'm just going to throw in 1,000 here. So 1,000 times mass times g. That's going to be divided by the impulse, which in this case, for the impulse here, if we, I think it's like 748,380 newtons for running 2 Bobcat engines on the first stage. So just simplify that down to mass times acceleration due to gravity divided by 748.38. And again, that mass, tons, so this needs to be in kilonewtons, in other words. So if we lock the throttle to this amount, mass will be changing, but if we lock throttle to this number, the kOS will keep on updating the amount of throttle needed to keep up with the way the mass is changing as you burn fuel. In terms of the suicide burn itself, it's been too long since I took physics, so I just Googled the equation for it, and that equation is 2 times acceleration times the distance to stop is equal to the difference between your final velocity and your initial velocity squared. And so these are not really terms that are usable in kOS though. So we have to do some substitutions of things that we do know, like we know force equals mass times acceleration. So acceleration is, in other words, the thrust of the engines divided by mass of the rocket. And again, as you burn fuel, that mass changes. So we can plug in values for sea level thrust, but we're just going to keep this term in because it turns out kOS has a built-in variable for mass. And so I'll shuffle this around a little bit. It'll be the difference in velocity squared divided by 2 times the acceleration. Now, we need to fix this acceleration term though, because this equation is just a generic equation for the time to stop, like for a car, but we're falling through there. So this needs to be h, the height, the altitude we need to start the suicide burn at. So we know the difference of velocity, but this acceleration term, this will be the acceleration, but minus 9.81 meters per second, because the craft, even under engine power, will be constantly accelerating due to gravity. And so this is the furthest we can simplify. Via testing, what I found was that you can kind of, through trial and error, find the velocity. And if you just assume the final velocity is 0, actually I'm not going to go all the way down to 0 because we would still want to be falling gently. Add a throttle setting that we can set using this expression. We want to be falling gently, but let's just simplify it and say it's 0. And normally the rocket, of course it depends on the rocket, but normally the rocket will be falling at around like 230, 240 meters per second. And we know the thrust. So what I'll do is I'll just simplify this down. So through trial and error, I found it's roughly around 50 times the mass. And mass is in tons. So if the rocket weighs 10 tons when the engines start up, it'll start the burn at 500 meters, in other words. So this is just an approximation. And I found this by trial and error. I put in the actual values. The rocket crashed, because it isn't a perfect equation. But it almost didn't crash. It came down very close to a perfect suicide burn. So I just increased it. I think it was like 48 or something like that times mass. So I just put it at 50 times mass. And the advantage of doing this is that gives it time it'll do the suicide burn, it'll come down, and then it'll gently descend a little bit, coming into land, and at like 5 meters per second. And you can change that using the code, but it'll just gently descend at a certain amount. And I found that going from 48 to 50 just gives it a bit more time to descend at a throttle setting that we have solved for already. This throttle setting, once it gets down to like 5 meters per second, we can just hold it at this throttle setting using the code. So I can write all this out. I can talk all I want about the code, but best to actually see the code. And so I'll pull that up. Okay, so here's the code. The first section here is just for the takeoff. This is the steering and staging. So I just lock it to up basically, and then I lock the fins so that the fins won't be doing any steering. And then I set the throttle to 1, which is 100%, and it'll stage, start up the engine, start gaining speed and altitude. And then what I do to start the turn is just wait until it hits a vertical speed of 70. That's pretty arbitrary. It doesn't have to be 70, it could be whatever value. And then I lock my steering to this heading. What this is an expression that will lean the pitch over as you gain an altitude. So you can see this altitude here. The closer I get to 70,000 meters, 70 kilometers, the closer this expression will be to 1. So you can see it says 1 minus this expression that gets closer and closer to 1 as you gain altitude. And then this is just to slow down that pitch rate. So if you graph it, it's like a curve times 90. So really what you're doing is you're just making the pitch slowly increase. And you can plug this into like Desmos and you can look at the curve it creates. I just like this because it's a simple way of programming the gravity turn without needing like a long list of, okay, now pitch 10 more degrees, okay, now pitch more 10 degrees, pitch more 10 degrees, pitch more 10 degrees, all the way down. This is just a way of, having it do the work for you. Then when it's leaned over, and it depends on the payload, how long you want it to run before you stage and do the boost back burn for the first stage. So what I did is I just said to wait until the delta V in the first stage is less than some multiplier times ground speed. And you can adjust this a little bit. For a lighter payload, maybe the multiplier might need to be higher, but this tries to take into account at least some of it by looking at the ground speed. The lighter the payload, the higher the ground speed will be by the time you stage. And so this is a way of adjusting for different payloads. So it can generally work. It's not 100% though, 100% accurate. This is just a simplification to make it easy to work. And so you might end up having to change the multiplier specifically here. For the next section, this is going to be the boost back. So this section is pretty important because you can't just do any boost back burn. You gotta land back at the Kerbal Space Center. And this bit of code here, these 7 lines of code, will make the booster hit the KSC. The rest of the code will be for the landing. So this just gets it on a trajectory back. So you lock the throttle to 0, and then stage. This will kick off the second stage. And then what I have it do is I have it lock the steering to a vector that only takes into account the velocity relative to the surface, so the horizontal velocity. And I had trouble finding a vector that would only point at against the surface velocity, like an anti-vector or whatever you'd call it. I had trouble finding this, so I just Googled this, and so what I found was to use a vector exclusion. So just what this is doing is excluding the part of the vector that is up of your velocity in general. So what this does is, with this little minus sign here, this means you're pointing retrograde because it has the minus, and you're ignoring the vertical speed. All you care about is the horizontal speed. So it's just a simple, elegant way of burning retrograde, but keeping your vertical speed. And then, because it's going to be maneuvering in space at that altitude where it stages, or near space, upper atmosphere, have it toggle the RCS. And then I have this term here, wait 15 seconds. You can change that depending on the rocket. It just takes some time for the RCS to swing the rocket around to this vector. And then 15 seconds is normally enough to get it on that vector and then burn full throttle until the ground speed goes to basically 0. I just said 11 meters per second, just by trial and error, because sometimes it doesn't go down to 0. I tried 10, but 11 is more reliable. It depends on the rocket. Just play around if you're using this with a different rocket, the script with a different rocket. But if you're using for the same rocket, it should work. It is trial and error for this value. You can always change it if it doesn't reduce your ground speed enough, or if it stops working. The way you could tell it stopped working is if the ground speed goes down to like 12, for example, and then starts increasing again. So if you see a problem like that, just make this number whatever you saw, like 12 meters per second, or whatever it is. So then it'll lock the steering back towards the Kerbal Space Center, and it'll start burning back to the Kerbal Space Center. And I have it wait until the speed is more than 175 meters per second. Normally it cuts off at like 178 or so, just because the acceleration is pretty high because the rocket is mostly empty when it stages, and so it accelerates quite hard, and so it ends up overshooting this value a little bit. But that just means that the velocity relative to the planet will be 0 because the planet spins with a velocity at the surface of 175 meters per second. For Earth, that value would be about 1,000 miles per hour. So basically, once you cancel out all your horizontal velocity, including the velocity that you got from launching with the rotation of the planet, then lock down the throttle, and what I did is I locked the steering to up, and this just points the rocket straight up. Give it some time to point straight up, give it some time for the RCS to work, and then I just had the throttle increase to 1, and using the equation we solved for earlier, this section here is the distance, longitude, just the difference between my intended landing site and the ship's longitude. So this is the longitude of the landing site, longitude of the ship. Difference times around 10 kilometers is your distance, because this will give you degrees of longitude, and there's around 10 kilometers, around 10.5 kilometers of distance per degree of longitude. Of course, this is a lot smaller number than it would be for Earth, but this is true for Kerbin. So that equation we solved for earlier, just plug in the terms here. This is distance, and then this is the 175 meters per second, and then here's the ETA to the apoapsis, because it'll take some time to fall outwards. And this is g divided by 2. So once it's burned up to the apoapsis high enough that it'll take a long enough time for the planet to rotate underneath it, so it'll fall down onto the KSP, then lock down the throttle, turn off everything, activate the grid fins, and then here, you don't have to, but I have it go down to 2 engines rather than burning all the engines for the landing burn later. Now, this section is the aerodynamic steering. And the reason I did it this way is so that I could use these PID loops for later for the landing burn as well. So I just set up these PID loops that'll be kind of multi-purpose PID loops. PID loops will just look at the difference between my set point here, my latitude and longitude set points, and give it a pitch input to the rocket of a certain amount between the range of these two values, so plus 20 degrees pitch, minus 20 degrees pitch, so that it'll steer towards the set point, which is the latitude and longitude. This is latitude, this is longitude, times 1000. The reason I multiplied it by 1000, because it should be 74 point so-and-so, like longitude here. The reason I multiplied it by 1000 is because the PID loops are easier to tune if it's like a larger number rather than a very small number. Like for the latitude here, 0.0972 degrees of latitude is not much to work with. So larger number makes it easier. See that this is the latitude of the Kerbal Space Center, and it times 1000. And that latitude is not very much, so I need something that is a big enough value that I can tune the PID loops for it, and still have the PID loops work for the landing as well. And I have the ship just float down until 35 kilometers, and once it hits this altitude of 35 kilometers, then it activates the aerodynamic steering. So what I did here is I just had it locked to the up vector relative to the surface plus another vector, and this is just a custom vector, 0, and the whatever the output of the PID loops is. So like here, this is the output, this is the longitudinal output, this is the latitudinal output. So it starts off as 0, and if the rocket is not falling right down onto the destination, the KSP, these numbers will increase. And this is vector addition. So the up vector plus a little bit of a difference to make it steer. Hopefully that makes sense. And next, the next section is for the landing itself. So I solved and I approximated a equation for the suicide burn, roughly around 50 times the mass. I have this in here because the mass is changing. And what I did with this term here is I said to steer until you hit this altitude. So it does the aerodynamic steering until this point. Then I lock to a very specific vector, which is the position of where I want to land, or rather a vector from the position where I want to land, plus 1,000 meters above my current radar altitude. The reason I did this is because if the rocket is a bit off position, it'll point towards the landing spot and up a little bit. So basically this will just lock the steering to a position vector and make it lean towards that position. So this isn't active steering, this is just an approximation. So I can switch from the aerodynamic steering to active steering. This is just a placeholder. Get it pointed in roughly the right direction, then moved on to the next thing, which is to start the engines, open the landing gear, and turn on the RCS, and it will run the engines until the vertical speed drops below 13 meters per second. Now, when I was writing down when I was solving for a lot of equations earlier, finding the expressions to use in this code earlier, I said it'd burn until like 5 meters per second. What I meant to say was 13 meters per second. It'll cut off the engines once it drops below 13 meters per second. This is quite interesting because initially when I was testing out this code, I just had vertical speed. But the thing is, it needs to be absolute value of the vertical speed. That's what this is. The reason being is sometimes it'll reach the speed you want and then not quite drop below 13 or the vertical speed here would be negative because it's falling. So it won't ever get below 13. So I just have the absolute value to make this a scalar rather than it being positive or negative, depending if it's falling or climbing. What I was talking about earlier was not so much that it wouldn't reach this speed per se, but it would come down and then start climbing again. And this is quite funny to watch. So that's what I meant to say, is because this is a negative value and I want to get it below that certain value there, I just have the absolute value of this number here. And then the next one is for hovering, basically. I have it lock the throttle to a setting where it's just going to maintain at 13 meters per second. It normally overshoots 13, as in it drops below 13, like down to 11. Just delay, to switch the throttle settings from 1 to this expression, which we solved for earlier. What that means is it's coming down, it's done its suicide burn, and it gets below 13 meters per second. And then it just maintains somewhere around there. And this allows it to adjust for the changing mass of the ship as it gently descends. So the whole point of doing this is to make the rocket gently descend towards the ground. In the meantime, I bring in the PID loop again, and while it's gently descending, I do a up vector and then the minus, because again the whole idea is to have it point retrograde, hence the minus. And so the PID loops will start. The PID loops will start adjusting, like between these values here, so that it'll head towards the landing zone. So I'm subtracting from the up vector this time, because instead of adding to the up vector like earlier, because this time I want to be making adjustments, pointing the top of the rocket towards the position I'm aiming for, rather than earlier where I was pointing the bottom of the rocket towards the position we want to land in, because now it's flying sideways under engine power. The rocket's translating sideways. And then the next part is to evaluate the PID loops using this section here until my the absolute value of my vertical speed is less than 5 meters per second. And again, vertical speed is negative, so I just use absolute value, so that is a scalar quantity, and it doesn't have any direction information anymore. Below 5 meters per second, then it will lock the throttle to 0. And because sometimes the rocket might try to tip over a little bit if it had some horizontal velocity, then it just lock the string to up, so that the RCS, which is let's see, turns on during the suicide burn. The RCS turns on during the suicide burn. It can use the RCS to keep it upright. And then this term doesn't really matter. This just gives me time to turn off the script, because if the script ends at this point right here, the throttle will go to 1, and then it'll start climbing again. Once the code ends, basically it just takes off in a straight line upwards, and this is not what you want.